Hello, good afternoon. Let's continue with our discussion on heredity. So, just to quickly recap, last time we talked about how genes can have different versions, and these different versions are called alleles. Okay, and so the example I used for you was big B is going to be brown eyes, and small b is going to be blue eyes. We use the capital letter for the dominant trait, and we use the lowercase letter for the recessive trait. It is important to remember we always use the same letter for a specific character. Okay, you're not gonna, for example, if we're talking about red flower and white flower, we cannot use R for one and W for another. Okay, like the question is not going to work out if you do it that way. So make sure you choose the appropriate letter for the question and to use capital letter for the dominant trait and lowercase letter for the recessive trait. Now we are diploid, meaning we have two sets of chromosomes, so we can have two alleles at most for a particular gene. So we can have big B, or big B, or small b, small b. So the genetic makeup would be the genotype. And then the phenotype would be the manifestation of the alleles, like the actual physical appearance. So for big B, it is going to be brown eyes. All right, this one also brown eyes because the big B is the dominant trait. So when it's combined with the recessive allele, it covers it up. The recessive one, it's not going to show up. And so if someone is little b, then it's going to be blue eyes. Okay. People who have the same allele on both chromosomes, we call them homozygous. Okay. Another word for homozygous is pure. And people who have different alleles for a particular gene, then we say they are heterozygous. It is possible uh, another word for heterozygous is hybrid. It is possible to be homozygous for some genes and heterozygous for other genes. Okay, whether you are homozygous or not for one gene has nothing to do with whether you are homozygous or not for another gene. These are independent events. Okay, so with that in mind, let's solve some genetic problems. Number one here, these are just from the PowerPoint slide. I just move it over to the OneNote here so it's easier to post afterwards. If a red flower is dominant over white flower for a certain type of orchid, write the genotype for the following flowers. Right, so homozygous red flower. Now, in this question, it didn't give you what letter to use for the trait, so you have to come up with it yourself. So tell me, what's an appropriate letter to use to represent the flower color here? Yeah, so we can use big R to represent red flower, and we can use small r to represent white flower. Remember to use the same letter, but uppercase for the dominant trait and lowercase for the recessive trait. Okay. Now, I mean, you're not going to be submitting any written work for me, but when you're doing a question on your own, when you're practicing or when you're doing it on, on a quiz or something like that, please choose the letter like appropriately. I mean, I've seen people choose like O, and that is a terrible choice. Okay, so Like even if the trait is like orange or something, don't choose O because like sometimes you keep on writing and then sometimes the big O and the small O and then like you can no longer tell after a while. Okay. And it's just confusing, right? For yourself and for the person who's marking it. Okay? So choose something that is appropriate. Okay. All right. Homozygous red flower. Okay. What would be the genotype for a homozygous red flower? What homozygous means is the same allele, and red would be big R, big R. All right, so take a moment, try B, C, D. I'm gonna give you like a 1 minute, and then we will take it up. Okay. Now, if you're watching this online later, there will be a lot of pauses during the recording. Okay, because I'm letting people try the question, so just fast forward yourself. Okay. Okay, homozygous white flower. What does homozygous mean again? Anybody? Can someone tell me what homozygous mean? Okay, yeah, sure. Another word for homozygous is pure, but what does it mean? Yep, so homozygous means same allele. Okay, same allele. Either they're both uppercase or they're both lowercase. In this case, they want a homozygous white flower. According to what we wrote here, the white flower is going to be small r. So small r, small r. Again, you're not going to use WW, okay? You have to use the same letter for the solution to make sense. Okay? Like it may not seem like a big deal, but but it is a big deal, okay? Because if you use different letters, you're gonna confuse yourself when you try to solve the problem, and then you're gonna get the wrong answer. Okay? Heterozygous red flower. What is heterozygous red flower? Participate if you can. Even if you private message me, it's fine. That way I know if you're getting it or not. Okay. Heterozygous red flower. Heterozygous means different. And so, yeah, that's correct. This would be big R, small r. Okay. Big R, small r. All right, so it's heterozygous because they're different. It is going to be red because red is dominant, and dominant will cover up the recessive trait. Okay, what about heterozygous white flowers? Anybody have an answer for that? Heterozygous white flower. Okay, now this one is a little bit tricky, okay? Heterozygous means they have to be different. So one has to be big, one has to be small. However, if you have one big R and one small r, then it's not going to be white, right? It's going to be red, as we saw in part C. So it turns out this is not possible. Not possible. Okay. So what's the point here? The point is if I tell you the phenotype of a recessive trait, then you know for certain it has to be pure. Okay. Recessive phenotype must be homozygous. Okay. Whereas a dominant phenotype red in this case. It might be big R, or big R, small r. Okay, moving on. Consider a type of orchid where red flower allele big R is dominant over the white one. And then I gave you the letter this time. Predict the phenotype and genotype of F1 generation when hybrid red is crossed with white. Okay. So I already gave you the alleles, so you don't have to create your own. But what is hybrid red? In the previous example, hybrid red would be big R, small r, right? Big R, small r. Cross means to breed and have offspring with a white flower. Okay. Now you look at this and you're like, hey, you don't tell us if it's pure or hybrid. How are we gonna do it? Well, if you pay attention in the previous example, it's white, and white is recessive, and there is only one way to create a white flower. It has to be little r, little r. Okay, so these are the parents. Parents, P generation. Once you've established that, then you can go ahead and do the Punnett square. Okay. Oh, hold on, the pen is a little bit weird. Just give it a moment. It needs some time to reset itself. But in the meantime, you can try to create the Punnett square. Can I type? Is it gonna let me type? Oh, Punnett square. Okay, so Punnett square is like that table, right? Let's try that again. There we go. There is the Punnett square. The tic-tac-toe. So here, for the hybrid red flower, it has a big R and a small r. So I can put the big R here and the small r here. Again, it doesn't matter if you put it on the side or if you put it at the top. Okay? It's not going to change the answer. Okay. And then for the small r is going to look like that. Do you understand how to set up the table? Okay. The whole class will, like today's class, will revolve around setting up the table. The table is going to get bigger and bigger as we get do like harder and harder question. So I just need you to understand how to set this up. If you're not sure, please ask now. Okay. Now, once you set up the table, it's just a matter of putting the letters together. So that's big R, small r. Always put the capital first. And then this one is small r, small r. Bring the big R over. Bring the small r down. Small r go here. This small r goes down here. And that's the result. Okay. So the genotype is the genetic makeup. We have two variety here. We have big R, small r. That is 2 out of 4 boxes. Okay. Or 50%. And 2 out of 4. 2 out of 4. Also 50% that are small r, small r. So that's the genotype. That's the genetic makeup. The question also asks for phenotype, which is what they look like. Now, genotype and phenotype may be the same sometimes, maybe not in other cases, okay? So in this case, it's the same, right? 50% big R, small r is red because big R is dominant. It will cover up the white allele. and then we have 50% white. That's how you do it. Any questions? All right. So it's a little bit harder online. This morning I had the same lesson in person, and then I was able to walk around the classroom and see, what people are doing, but obviously I cannot do it with you guys in a virtual environment, but I do encourage you to try this out. Okay? I'm gonna give you 4 minutes to try this. And if you have the answer, just message me. Okay? I'll tell you if you get it right or not. Just private message me, and then I'll let you know. Okay? 4 minutes. Go. Okay, I'm just give it another minute. I got a few responses from people. If you have your answer, please send it to me. And if you don't know how to do it, you can let me know as well, okay? Don't leave me in the dark here. All right, let's take it up. We have pure red, which means it's big R, cross with white. White is little r. And then you can go ahead and set up the Punnett square. Big R goes to the side. And again, it doesn't matter if you do it at the side or at the top. Uh, it's not going to change the answer. So then you combine the letters and you can see that it will be 100% big R, small r, or 100% red. Okay. So this goes back to what we were talking about last class. If you start with pure parents for a particular gene, okay, all of the next generation will have the dominant phenotype. Okay. So let me give you another example here. Let's say I have a mouse here, and then I have another mouse here, and this one is gray, and then this one is white. All right, and we're gonna breed these mice, right? And they are both pure. Yeah, they're both pure. And then afterwards, we look at the babies. Okay, look at the babies. Okay, and then all the babies are gray. So which one is dominant? Is white dominant or is gray dominant? Well, I hope the answer is obvious. This is dominant, right? Yeah, exactly. All right. So again, this only works, and it's a big only. This only works if both parents are pure to begin with. Okay. It wouldn't work if they're not pure. All right. So sometimes in a question, I'm not gonna tell you explicitly which one is dominant, which one is recessive. Instead, I will say, okay, two pure parents, one with white coat, one with gray coat, was bred together, and then all of the offsprings have gray coat. Based on that information, you should be able to figure out gray is dominant. So this would be like big G, and this is small g, small g. Okay? Do not use different alphabets. I keep on saying that because every year, despite me repeating this multiple times, people use different alphabets and then they do the question wrong. Don't be that person, okay? All right, that's all the examples for these are called monohybrid questions because we are only tracking one tray at a time. In the study guide, which by the way I think I already posted the answers, there are more monohybrid problems for you to try. Okay? There's the solution I work it all out for you. So like if you're stuck, you can look at it and see how it's done. We will have some time next week as well. If you have a specific question you want me to go through, we can do that. Um, like obviously we don't have time to go through all of them. So you do your homework and then you let me know which one you want to take up. If nobody makes any requests, then I'm just gonna move on and do other stuff. All right. Okay. We have more things to learn now. Okay. This here is a family tree and it's called a pedigree. Pedigree. Family family tree. Right? So pedigrees are useful to help us keep track of certain traits that we are interested in, to help us keep track of diseases in some cases. All right. So the inheritance pattern um, refers to how the trait is being passed on. Right? There are different ways to pass it on. For example, the trait can be autosomal dominant or recessive. Autosomal means it is passed on in chromosome 1 to 22. Okay? Like it's on one of those chromosomes. If it's passed on in the X or in the Y, then it is called sex-linked inheritance pattern. I don't think we have time for a sex link today. We'll do it next Monday. Okay? And whether it's dominant or recessive is going to it's gonna look different on the pedigree, right? So for us, I want it's already complicated. Okay, so I want to keep it simple for you. if I give you a pedigree and I want you to figure out the inheritance pattern, it will either be autosomal dominant or autosomal recessive. Okay, I'm not gonna throw in the sex link and stuff in the pedigree. Okay, so you only have two choices when you look at a pedigree. When you study a pedigree, you only have to tell me whether it's dominant or recessive. So, how do you tell? Well, some information first. Okay. Square means male. Circle means female. This means have kids together. Okay. And sometimes you might see diamond. Diamond is unknown. Right? Like if a couple like if the mother is carrying a baby but she hasn't find out the gender yet, then it's unknown. Then you put a diamond. Okay. So these are the basic symbols for pedigree. There are more complicated ones for like twins, identical twins, fraternal twins, so on and so forth. But that's all we have to know for now. These Roman numerals, they are generation. So generation one, two, three, four. And within the generations, we use Arabic numbers for for the individuals. Okay. So what do we call this person? This person is 2-4. Generation 2, individual number 4. Okay. This person, 3-5. Okay. You need to know because on the test or quiz, I'm gonna say what is the genotype of 4-1? Then you have to know I'm talking about this guy. Any question about the shapes and the numberings?
What about the dark?
What about this? Oh yeah, the shade in, right? Yeah. So if it's shade in, it means they have the trait you are studying. Okay. Like if I'm studying blue eyes or something. Okay. So everybody who has blue eyes are gonna get shaded in like that. Okay? If I'm studying a disease like you know sickle cell anemia or something, these are all the people who have the disease. Okay. We'll talk more about diseases later, but that's about it for now. Okay. These are, I guess, great grandparents. I want to ask you, how many kids did they have? How many kids does 1-1 and 1-2 produce? Look at the pedigree and let me know. 3 kids would be correct. Let's trace it. Okay. That's 1 daughter, 1 son, and then another daughter. Okay, that's not their son. That's the son-in-law. Okay, see, it's not connected, right? Okay, that's the daughter-in-law, and then another son-in-law. Is that okay? All right, I'm gonna erase all these stuff. Now, here's a question. That's the difficult question to ask, right? To answer. Uh, Based on this result, the trait we are studying, whatever it is, doesn't matter. Is that a dominant trait or is it a recessive trait? So like you wouldn't know, right? So you make a guess, right? Let's say it is dominant, okay? Let's say it is dominant. Okay, don't copy this. Just watch and then try to understand it. It's because I'm gonna be writing stuff and erasing it. There's no point of you copying. Right? So dominant, let's say it's dominant. Okay? So if it's dominant, that means the people who have the trait, the people who are shaded in, they will have at least one capital letter, right? So we can use A as our allele. Okay. So this person has the condition. if it's dominant, then he must have a capital A. Now, we don't know if he's big A, or big A, small a, right? We don't know. It could be either one of them. But where did he get the big A from? Well, the big A has to come from either the dad or the mom. Okay, let's just say it came from the mom. Okay? You can trace it back and say, oh, the big A came from the mother. But we take a look at the mother here. The mother does not have the same trait as the son, right? And if this was a dominant trait and she has a capital A, then she must also be shaded. But we don't see that. She's not shaded. And that tells you it's not possible for this to be a dominant trait. Okay. Because if it's the dominant trait, then at least one of the parents has the same trait as the child. Okay. So if you see this kind of pattern, if you see a situation where the parents don't have it, but one of the kids has it, then it is definitely not dominant. And if dominant and recessive are the only choices, which is what we're doing, okay, then it must be recessive. Okay? So both parents, if both parents do not have the trait, they're not shaded, and at least one of their children has it, then the trait is recessive. Okay? I'll let you copy it first, and then I will explain more. But as usual, I invite you to ask questions. So that means this must be recessive, right? Okay, so let's take a look at how this works. Recessive, that means anybody who are shaded in, they must be little a. And that's the only way to express a recessive trait. So how is it possible for someone to have the little a and little a, but then the parents don't have the condition? What, based on this um, pedigree? Oh, yeah. Thank you, Vicky. You answered my question before I figure out how to ask it. So how is this possible? Right? Well, it's possible because the parents are hybrid. They're heterozygous. Okay? So they don't have the trait, but they carry the recessive allele for it. Okay? So that's the only way where this is possible. Now let's take a look at the other kids. This one is the daughter, and she does not have the trait, so she must be capital A. Right? But we cannot say for certain whether she's big A or big A small a. Okay? We have to do more detective work. But we'll leave it at that for now. Okay. Same thing over here. This one is big A something. Big A something. Now, if we trace another generation, look, if we go down in another generation, these people have a son that has the trait, which means this guy, number 35, it's little a, little a. So one of the little a must have came from the mother, and then the other little a is going to be from the dad, right? So based on this, we can conclude she's definitely big A, small a. Does that make sense? Any questions? What about who though? Who are you talking about, Elvis?
The parent.
Which level? Which generation?
First one.
This one?
Yes.
What about okay? So what's the question? Ask me again.
Yeah, if one parent is a recessive pure homozygote,
I understand your question. You're saying like could they be big A, small a, and then what's the other one?
small a.
No, but that's not possible, right? Because if one of the parents is small a, we would see her shade in, right? But she's not
Right.
shading. Yeah, so
Yeah.
that's why like it's not possible. Okay. Okay. Let's try another one here. Now, is this dominant or is it recessive? Well, over here we see two parents have the situation. They have the trait. Okay, doesn't have to be a disease. It could just be a trait, right? Okay, we don't know what it is. Doesn't really matter. So let's see. Like, is it recessive? Let's try. If it's recessive, if the trait we're looking at is recessive, then what's the genotype for this guy? What's the genotype of this person if it is recessive? Okay, yeah, it's little a, right? That's the only way for you to express the recessive trait if you have that to have both of the alleles, right? That means the mother here is also small a, small a. Now, if that's the case, if the father is small a, and the mother is small a, then what can you say about the whole family? The whole family should be 100% small a, right? But if you look at their kids, this guy does not have the trait, which means this cannot be recessive. Do you understand? Because if it was recessive, then this would be shaded in as well. Okay. So the telltale sign here for not recessive is if you have two parents that are shaded in, and then at least one of the kids are not. So if both parents have the trait and at least one of them and at least one of the children, one of their children does not have it, then the trait is dominant. Okay, I have to emphasize. All right, this only works. This only works if there are only two choices for you. Okay? Like if you have to pick between autosomal dominant or autosomal recessive, then you can look for these things. Okay? Keep in mind there are other inheritance pattern. Okay? Like sex-linked, sex-linked dominant, sex-linked recessive. Right? We haven't considered those. Okay? So this must be dominant. This must be dominant. Right? Dominant. Right? So that person must be big A, small a, and this is small a, small a. Okay? So would it? Yeah, okay. Yeah, it wouldn't be big A, okay? Because if both of them are big A, then they wouldn't have a son that doesn't have it, right? For them to have a son that doesn't have the trait, they have to they have to be heterozygous. Okay? Which brings out an important point. Sometimes if you see things like this, okay, let's say they have it and then both of the kids have the trait as well. Like this is inconclusive. Okay? You don't know. I mean, they could be both big A, and then the whole family is big A. That's dominant. Or they could be small a, and the whole family is small a. Right? So, like in a situation like this, you need to look at the bigger family tree in order to figure out what the appropriate, um, like what the inheritance pattern would be. Okay. So you guys understand how when you have a dominant trait, you might have like a hidden recessive trait, right? You wouldn't know about it, right? Because it didn't show up, right? But then if you see it in one of your kids, then you know you have it. Like I have black hair. My wife also has black hair, but one of my daughters have brown hair. Okay, people think she dyed her hair. Okay, but like no, she actually does have brown hair. So that means I probably have like a recessive brown hair allele in me, and so does my wife. And 25% chance. Okay. Uh, Same thing with my sister actually. Sister has black hair. Her husband has black hair, but one of their kids also have brown hair. So maybe it's a common recessive thing um, for our family. Are we good, guys? Thank you, thank you. I have this burden in me to because I always feel like you know I'm not conveying the information uh, virtually, and it's hard for me to tell. So I
Sure,
always
you're
keep
doing a
on
good job.
asking.
If we didn't understand, we would ask.
Oh, thank you, thank you. Hopefully, the rest of you feel similar. Okay, so we have this study guide question, which is number 6. And why don't you take a moment and figure out what the pattern is? Again, you only have two choices. Okay, it's either dominant or recessive. Okay, let's try to figure it out and let me know. All right, what is the first one? Anybody? These are three separate families. Okay, what's the inheritance pattern for the trait of interest in this first case. Let's do a poll. We haven't done those for a while. A for dominant, B for recessive, and then there is always the not sure button if you want to use that. All right, we have a 50-50. Half of you who participated anyways, said is recessive. The other half says is dominant. Well, let's take a look at the class notes. It says in bubble letters here, if both parents do not have the trait and at least one of their children has it, then the trait is recessive. Let's take a look at what we have here. The parents don't have it, at least one of their kids has it. This must be recessive. That's all. So this is little a, little a. How come she has the trait when the parents don't have it? The only explanation is if they are hybrid, right? We cannot say with certainty what the siblings are, but we know they have to have at least one capital A because they don't have the trait. All right, number two here. Number two here. Dominant or recessive? Let's try the poll one more time. Okay, unfortunately, we continue to have 50-50 split in the answers. Let's try this again. So we see here, I mean, there are different parents here, right? There are parents here and there are parents here. It's inconclusive if you look at this family, okay? Because like, one parent has it and then the other parent does not. It's hard for us to decide whether it's dominant or recessive. However, if you focus on this family, the parents both have it, whatever it is, okay? It's just a trait you're looking at. Both parents have the trait, but none of their kids do. And so, let's see what we roll over here. If both parents have the trait and at least one of the children does not have it, then the trait is dominant. So the answer for this is dominant. Okay. It couldn't have been recessive. Okay. Let me try to explain to you why it cannot be recessive. If this was recessive, then these parents must be little a, which means all of their kids should have been shaded in because that's all they could pass on, right? But none of the kids are shaded in. So this is not recessive. This must be dominant. Okay, big A, small a, big A, small a. And it just happens that none of them receive the dominant allele. Okay. Now there's a son-in-law here. He has the tray, so he's capital A for sure. But is he capital A, big A, or is he big A, small a? How do we know? Well, let's take a look. They have a child that does not have the tray, so this child must be small a, small a. One of the small a came from the mother, the other one must have came from the dad. Okay, and these people must all be big A, small a. Big A from the father and small a from the mother. Here, I'll highlight it for you. Okay, and then over here, one of the small a is from the mother, the other small a is from the father. Questions? All right, we have one more shot at this. Make me proud, guys. What is this last one? Dominant or recessive? Okay, choose something, please. Choose something. Okay, I feel better. Right? We have 90% who got the right answer this time. This is recessive. Okay, how do you know? What's the dead giveaway that this is recessive? Well, the parents don't have it, but one of their kids do. Okay, same thing over here, right? Understand? Now, another thing that might be overlooked here is the fact that generally speaking, if it's a dominant trait, then it shows up more often. Whereas if it's like a recessive trait, it tend to skip generations, right? Like, you have three generations that doesn't have it, and all of a sudden it shows up, right? That tends to be uh, uh, a characteristic of recessive inheritance. Okay. All right, let me see what's going on next. Yeah, you know what? Let's take an early break because the stuff afterwards is pretty heavy. Yeah, I mean, this is heavy already, and the stuff coming up is even more confusing. Let's take five. We will come back at 1:30. All right? See you in a bit. All right, here we go for round two. So far, what we have done so far is to look at the inheritance pattern of a single trait, right? Flower color, or we look at, brown eyes, blue eyes, and whatnot. So the next step is to track two traits at the same time, right? Two traits at the same time. So just like a couple slides here to get we all set up, and then I'm gonna write more notes for you. So when we try to track two things at the same time, then it is called dihybrid cross as opposed to monohybrid cross. So in this example that we're going to be doing in a second, we are once again looking at the peat plants that was used by Mendel's in his pea plant experiment. And we have two dominant traits here, which would be round being dominant over wrinkle, and then yellow is dominant over green. So the two traits we're looking at would be seed shape and seed color. So let's start with pure round yellow and pure wrinkled green. Right? So the parent generation, everything is pure. And in case you missed the last class, right? Like how did he know that these parents are pure for round and pure for yellow? He would look at the plant and self-pollinate the plant for a couple of generations. And if they always produce round seed, then it's a reasonable assumption that the plant is pure round. If they always produce yellow seed, same thing. It would be reasonable to assume that it is a pure yellow plant. Okay, so we're going to start with a pure round yellow and a pure wrinkled green plant. We will revisit this. But first, Mendel has a second law, and it is called the law of independent assortment. Okay, law of independent assortment. His first law was law of segregation, which tells you the allele separates during meiosis, and the gamete will only inherit one of the alleles. Okay, if it's big B, small b, the allele, the gamete will either get the big B allele or the small b allele, right? That is basically how we set up the Punnett square, okay? The second law is independent assortment. Let me read it to you first. The alleles of two or more different genes get sorted into gametes independently of one another. So whether let's say someone has big A, small a for one of the a gene, and then big B, small b for another gene. Right? We check tracking. We're tracking two separate genes here. So for the big A, small a, because of the law of segregation, then the gamete will either have the big A or it will have the small a. Okay? That part you understand. But whether you inherit the big A or not will not affect whether you inherit the big B or the small b. In fact, the big A could pair up with the big B, okay? Or the big A can pair up with the small b. Similarly, if you inherit the small a, you might have a big B or a small b. Okay. So that's what the law of independent assortment means. Right? Each gene is sorted independently into the gametes. Right? Just because you're big A for one doesn't necessarily mean you're going to get the big B and big C and big D, so on and so forth. Okay. So let's take a closer look here and practice a little bit first. Right? Let's say we have the parent here, the parent, and let's say is big A, and then big B, small b. Let's practice writing the kind of gametes that will be produced by the parent here. Okay. So it's big A only, then I'm going to write big A. What can big A combine with? Well, big A can pair up with the big B. That's one possible gamete. You're not going to get big A in the same gamete, right? Because that would be non-disjunction. We learned about that last time. And you can only get one of the two alleles. So one of the A's and one of the B's. And you're trying to figure out what possible combinations exist. There's a, oh yeah, okay. So that's big A, big B. And then the other possibility is big A and small b. You can repeat with the other A, but you would just end up having big A, big B again. We don't have to write it twice. And then you would get big A, small b. Understand? Okay, let's try another parent. What kind, well, sorry. Let's do something a little bit different. What kind of gametes will there be? Try it out. Yeah, thank you. So this would be big A, small b, okay, and then another big A, small b, small a, small b, and then another small a, small b. Okay. And then just one more. Okay. I briefly did it on the PowerPoint slide. Let's see if you can do it again yourself. So big A, big B, big A, small b, small a, big B, and small a, small b. Okay. Four different possibilities. Okay. What if we track three traits? Right? Let's say someone is big A, big B, small b, big C, small c. How many types of gametes? Anybody? Okay. Well, you don't have to list them out. Okay. You can just do the math. So how many choices here? Two choices. Two choices and two choices. And I taught you this before. When you have, multiple choices, I guess, that you want to link together and you want to figure out the total number of combinations, what operation do I do here? You multiply. That's right. So 2 times 2 times 2 is 8 different combinations. Okay, I can list it out for you here to see. So it could be big A, big B, big C. That's one gamete. Big A, big B, small c. Big A, small b, big C. And I am missing one, and my brain is not really working. Um, oh, this one. There we go. Okay, so 8 different combinations. Okay, let's backtrack a little bit here. Only one choice here. It's either big A or big A, so really one choice. For big B, small b, two choices. 1 times 2 equals to 2. You have two possible gametes. Big A, small a, two choices. small b, one choice. Two possible gametes. 2 times 2 equals 4. 4 possibilities. Is that okay? All right. So this is what we're gonna do next. We're gonna try this dihybrid situation. Okay, so this is the P generation. You can try your best to draw this pure round and pure wrinkle green. Um, and we need to declare some variables, kind of like math. Okay. We already know this is dominant based on the table. So big R for round and small r for wrinkled. Okay, what's the other letter that I should use? Remember, we're tracking two different traits now. That's why we have two different letters, right? Sure, yeah. Big Y and what's the trait? Big Y is yellow. And therefore little y is green. This is the P generation. P generation. Pure round yellow. Big R, big R, big Y, big Y. Pure wrinkled green. What is pure wrinkled green? Yeah, little r, little y, little y. Let's write down the gametes. What kind of gamete or gametes will this plant be able to produce? Okay, yeah, one kind, and what would it be? Okay, so if you think about it, it's big R only, so guarantee a big R, and big Y only, guarantee a big Y, and that's the only one. Okay, I'm gonna put a bar here to separate the parents. How about for pure wrinkle green? No, same story, right? It can only produce small r and small y. So we're gonna do the Punnett square, but it's really small. This Punnett square actually it's just 1 by 1. Okay, so we have big R, big Y here, and small r, small y. You're not gonna do it like this, okay? Watch. You're not gonna do it like this. Okay, this is wrong. Okay, we do not separate the R and the Y because we are tracking them together, right? We're tracking them together. So this is wrong. Okay, so if you put it together, it will be big R, small r, and big Y, small y, which means
Uh, so can you cross it in red, please?
oh, sure, sure. Yeah, you like that better? So it will be 100% big R, small r, big Y, small y. This is the F1 generation. So 100% round and yellow. And this is the reoccurring theme I have been trying to tell you about. If the parents are pure and they look different and you don't know which one is dominant trait, you breed them and you see what the first generation looks like. The first generation, the F1 generation, will always possess the dominant phenotype. So I'm just gonna leave this for a bit. We'll come back to it. I'm gonna go to the side here, and I'm gonna do my mouse thing again. Okay. So here we have the parent mice. Okay. This one is let's give it a gray coat again. Okay. So this one is gray and long tail. This one is white coat and short tail. Okay. They are both pure. Okay. This thing only works if the parents are pure. I'm going to cross them. And we get 100%, 100% mouse like this. Okay? So which one are the dominant trait? Which one are the dominant trait? Is gray dominant or is white dominant? Well, if you look at the first generation, they're all white, so white is dominant. And then long tail in all of F1, then long must be dominant as well. Okay. So again, this is important information for you to tell which trait is dominant. If you're not sure, you see gray mouse, white mouse, and if they're pure and you cross them and you end up getting all the mice are white in the first generation, then white is dominant. You see long tail and short tail, and all F1s have long tail, then long tail is dominant. Does that make sense? Okay, let's go back to here. We have the F1 generation now, and all of them are round and yellow. So he did what he did with the one trait, but now he did it for two traits. So this would be the F2 generation. Okay, so he took the F1 and then cross the F1 generation together. Okay, cross F1 individuals. Let's write down the gametes. Okay. Probably should move this over there. If you have been following, then the gametes would be big R, big Y, big R, small y, something like that.
It's on top of.
What's that? I'm sorry. Okay, and then we're gonna put a bar here, and it will be the same thing. So how big is the Punnett square going to be? Well, we have four things on the side and four things at the top. It will be a 4 by 4 Punnett square, which is uh 16 in size. Okay. Let me try to do this. 4 by 4. There we go. Okay. So I'm gonna put the letters here. It's messy if I write it, so I'm just gonna type it out. R big Y. And let me see if I can make it bigger. Okay, and then same thing on the side, right? So please try to make the same table for yourself. Okay, give you a moment to do that. Okay, give me a second. I'm just gonna cheat a little bit here. There, it's bigger now. Okay. Do you understand where the letters come from? Right, so all this stuff goes here, and then all this stuff goes here, right? And now it's just the painstaking work of combining them together. So over here, big R, big Y with big R, big Y. It's gonna look like that. Okay, so I will do it, and you should do it too, and then we will compare answers at the end, okay? Just gonna make it bigger so we can see it better. Okay, don't do the genotype and phenotype yet, okay? Wait for me. Okay, give me a thumbs up if you have finished copying or trying it out yourself, and then we're gonna continue. Okay, now this one is too complicated to do the genotype, so we're just gonna go right ahead and do the phenotype. Okay, if you have a highlighter or something, please use it. This one, what's the phenotype? What is the phenotype for this first one? Just say it out.
That is round and yellow.
Yeah, it's round and yellow, right? Because big R is round and big Y is yellow. So I need you to go look at all 16 combinations and find out how many are round and yellow. Okay. Once you count all of them, let me know what number you have. How many round and yellow? Okay. I see 8. Anyone else? I see 7. Anyone else? All right. Both of you changed your answer. Let's see. Uh, this one is round and yellow. Basically, you're looking for anything with at least one capital R and one capital Y, right? So all these up here, they are round and yellow. Round and yellow for these one as well. And this guy is round and yellow, and that is also round and yellow. Okay, I think those are it. So if you count it, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of 16 are going to be round and yellow. 9 out of 16, if you key that into the calculator, it is um it is 56.25%. Okay, I need another phenotype. Anybody? Give me another phenotype. Like what's this one? What?
That is round and green.
That is round and green. Very good. Let's find all the round and green. Let me know what fraction we have. All right, there is another round and green here. Green is little y, little y. Round is at least one big R. So these are round and green, which means it is 3 over 16. And according to my calculator, it is 18.75%. Okay. How about this? What is the the phenotype for this one? This is wrinkle yellow. Yeah, wrinkle yellow. Very good. Wrinkled wrinkled and yellow, which is also 3 out of 16. 3 out of 16. And finally, we have the super rare wrinkle green. Wrinkle green. Okay, which is 1 out of 16, and that is 6.25%. Okay, so this actually creates what's called the 9-3-3-1 ratio. Okay, if you remember this ratio, it will save you a lot of time on some of the questions. Okay, what is the meaning of the ratio anyway? Well, the meaning of the ratio is if you start with if both parents are heterozygous. For two traits. Okay, so like if they're big A, big B, small b, okay, then always 9 out of 16 of them would be dominant for both traits. 3 out of 16 will be dominant for one trait and recessive for the other, or recessive for one and dominant for the other. And finally, this would be 1 out of 16 for recessive and recessive, which again should make sense because in order for recessive to show up, the dominant cannot be there. And that's why it's like super rare. Okay. So last example quickly. Back to my mouse situation. Okay. Let's go back here to the mouse. Okay. Maybe I give you a moment to copy this first. This 9331. Okay. I'm going to go back to the mouse here. All right. Here are the mice. Okay. So let's say I take F1 cross F1. Okay. And let's say we have 100 mice in F2. Okay. How many do you expect to be gray and have long tail? Okay. That's the question. I'll put it over here. All right, so let's do this together. We know the parents are pure, and then based on F1, we know white is dominant, right? So like big W is dominant, and then big L is like long is dominant, right? Okay. So white is dominant than gray. Long is dominant over short. That's how you know. Okay. And then all the F1 would be hybrid, would be big W, big L, small l. So now here it says F1 cross F1, which means it is going to be two of these things breeding together. And according to what I wrote here for you, I should probably like highlight it for you as well. So many important things to remember. You should reorganize the notes. If both parents are heterozygous for two traits, then you're gonna have the 9:3:1 ratio all the time, because then your Punnett square is gonna be 4 by 4, right? So it's asking you how many do you expect to be gray and long tail? So looking at our situation here, gray is recessive, and long is dominant. Okay. So recessive for one trait and dominant for another trait, the number is 3, right? If we are asking for dominant and dominant, then the number is 9. Right? So dominant, recessive, and dominant, it's 3, which means it is 3 out of 16. That's the expected ratio. And then you want to times 100%, sorry, times 100, not 100%, times 100, because there are 100 mice in the litter, right? So then you plug this into the calculator, 3 divided by 16 times 100. So you would expect approximately 18.75 mice. Okay. So obviously you cannot have 0.75. So, roughly 19. Okay. Roughly 19 mice. Okay. Last question. What kind of mouse would be rare in this situation? Right? What kind of mouse would be rare in this situation? Gray short. That's right. Gray is recessive. Short is recessive. So the probability of getting gray short is 1 out of 16. Right, so if you do 1 out of 16 times 100, in 100 mice, only about 6 of them will be gray coat with short tail. Okay, lots of work for you to go through. You have a question, Elvis? I saw you on mute.
Yes, yes.
Uh-huh.
So the probability is always the denominator is always 16, right?
Yeah,
When you
only if the parents are heterozygous, right? Because if one of the parents is not heterozygous, then the table is not going to be 4 by 4, right?
okay.
Yeah. So like, over here, we're going to talk more about this next time, okay? But let's say in another situation, if we cross this parent with this parent, then the Punnett square will only be 2 by 4, right? There will only be 8 slots in the table, right? Because there's only two gametes with four gametes, right? So it's not always 4 by 4. It's only 4 by 4 if both parents are heterozygous. Okay, so what I want you to do, guys, is to practice the monohybrid problems. And if you want, you can try the dihybrid as well. But next class, we will do a few more dihybrid problem. We still have to learn incomplete and codominance inheritance pattern, and then we have to learn sex link. That probably should take us the entire Monday class. Okay, but just in case we finish early, uh, bring the lecture 9 stuff as well. Okay, we're almost there. It's just I think 3 more weeks and then we're done. So hang in there. You guys are doing good. Enjoy the rest of your week. Bye-bye.
Bye, sir. Thank you.
Bye.
Bye, sir.
Bye-bye.